All right, to kind of conclude our discussion about how the integral can help us with probability, we're going to go back and discuss that special distribution I mentioned before, where we have the case that all three measures of centrality are equal. Now, we didn't discuss the mode in this class, but we could have. And you could imagine if this were a histogram that the most frequently occurring value is right here at the tallest point. And so here we know that our median and our mean are the same, and also the mode, just as an FYI. And when this occurs, it just so happens that each function, each probability density function that creates the normal bell curve shape here for this distribution has the same form. And so this is the form of each one of those probability density functions. It's a pretty complicated form. You're not expected to memorize it. You just need to know how to work with it. So it's 1 over sigma times the square root of 2 pi times the exponential function with this kind of complicated exponent here, negative x minus mu squared over 2 sigma squared. Now sigma is a new term. It stands for the standard deviation. And standard deviation means how far away from this central measurement that your measurements lie. And so depending on your standard deviation, you can determine how many values are close or kind of centered around this mean and how many values are stretched out. For us, we'll be given that information, and we'll be expected to be able to compute the probability or likelihood of an event occurring if we know the function has a normal distribution and we know some information about it. Like, for example, we know the mean and we know the standard deviation. We'll be able to compute the probability that something would occur. So if you've been following along in your handout, then the last example we're going to talk about is a pregnancy example. And so in this example, we're talking about the length of human pregnancies. So as it turns out, human pregnancies are normally distributed, and the mean for a human pregnancy is 268 days. So our mu here is 268 days. The standard deviation is 15 days, meaning one standard deviation is going to have some patients delivering pre-15 days or post-15 days of that mean, 2 standard deviations 30 days before and after. And there is a lot of work in probability and statistics on how that standard deviation makes this kind of peak skinny or fat or things like that. But for us, we're just curious on these two measurements so that we can compute the probability of something occurring. So in this problem, we're interested in the percentage of pregnancies that last between 250 and 280 days, which is, give or take 1 standard deviation from the mean. So this is what we're interested in, the probability that a baby is going to be born from a human between 250 and 280 days. And so we're going to be taking the integral from 250 to 280 of this normally distributed probability density function. So plugging in here, you can see I entered in 15 for sigma, and I entered in 268 for mu. Now, as it turns out, this is impossible for us to integrate by hand. Do you remember when we did Simpson's rule, we looked at e to the x squared or e to the negative x squared? There was no antiderivative for that, so we were stuck with Simpson's rule back then, if you remember, or the trapezoid rule, the midpoint rule. The best we could do was approximate. But now we have some computer-assisted programs to help us along with that. So I very carefully typed this into Wolfram Alpha or Mathematica, depending on what you want to use. I did try it in my TI-83 calculator, and my calculator got frustrated and quit. But when you put it into the computer, you get this value for the integral, which is an approximation, of course, 0.673075. That tells us that it's 67.3% likely that a human being would actually be born within 250 and 280 days, given our normally distributed pregnancy function. So I encourage you to kind of play around. WolframAlpha.com is the free version of Mathematica, and with some very careful keystrokes and some very careful kind of grouping symbols, you can get these values out from that. So this is our last example of the normal distribution, and again, you just need to be able to work with this formula. You won't be expected to memorize that formula. So I hope you enjoyed our lesson on probability.